Okay, thank you everyone for joining. I'm Hugh Yong from San Jose State University here in California, US. I'm with the electrical engineering, and my lab is a multi-physics and circuit lab. And thank you very much for inviting me to give a talk on the quantum computing. I will assume everyone don't have much background, so I will go from the basics. If I'm too slow, going with too much basic, just let me know, and then we can have a Q&A session. So today I will first give a self-introduction, and then we'll talk about the basics of quantum computing from the algorithm perspective. I hope to show you a real demo, a real online demo on how to use the quantum computer on IBM Q. And then this part will be the hardware, some typo here. I will just give a brief introduction on the quantum computing hardware, followed by conclusions. Just want to advertise a little bit first. I have a book which is Introduction to Quantum Computing from layperson to a programmer. So I do not expect you to have a very strong linear algebra background, and also I don't expect you to have quantum mechanics background. If you're interested, you should be able to download from Springer. I don't know if your school have a subscription. If you have, if you connect to VPN, you should be able to download the PDF for free. Okay, and it's also available on Amazon. And for this book, I have created some teaching material based on the class I teach here, and this is the link to the YouTube. You can search for Introduction to Quantum Computing on YouTube. You should be able to find it. I also have another set of YouTube that is about the quantum computing hardware and architecture. It's about how different qubits are implemented. You can also take a look. Right. So San Jose State U is in the Silicon Valley. We have a pretty huge student body, like 36,000 students. We are a minority serving institution, and in our school we have like about 800 or 700 master and undergraduate students. We don't have a PhD program at this moment, but we have a lot of foreign students come here for the master degrees, right? And in the master degree, we have a new specialization on quantum information and computing. The student need to finish three classes to satisfy the requirements. So we have this introduction to quantum computing is mostly for algorithm. Cryogenic nanoelectronics, later you will see that actually quantum computing is actually electrical engineering. Most of the part of it is electrical engineering. The quantum chip is only a tiny part. Most of them, we need to use cryogenic electronics to control them. And then another class is about the quantum computing architecture and the hardware. We also have a new program, Master of Science on Quantum Technology. So this is a program itself. So you will get a degree on Master on Quantum Technology related to quantum computing, quantum sensing, and quantum communication. It's sponsored by the National Science Foundation. If you're interested, you can visit the website to take a look. Right. And finally, again, the advertisement, you can download the book from here, and these are the two QR codes. You can find the video for the quantum computing and also the quantum computing hardware and architecture. If you need any information, feel free to send me an email. Okay, so I will go to the basics now. What is quantum computing, right? So I think many of you have heard about the importance of quantum computing. The most important thing that it has is that it uses two phenomena, the superposition and entanglement, which I will go into the details. And I will also say that interference is also very important. That's like what you learn in the wave mechanics, but it's the interference of the quantum state. So there are two types of quantum computers. One is the gate-based model. This is what we will discuss today. It is like the classical circuit, right? Most of you are electrical engineer. You know you have NOR gate, LAN gate, and then you can build a circuit, something like this, but not exactly the same. Particularly from left to right, this is not the space, right? If you're a classical circuit, this can be LAN gate, NOR gate. Then you lay out your chip. But here is actually the time. I will explain more later. So actually, there's some fundamental difference between the classical circuit and the quantum circuit layout. We can use this to and then develop some special algorithm and to solve some problem in exponentially fast speed if it works well. Another thing is also pretty important, and I feel that it might actually have the real application or commercial value earlier than others, which is the quantum annealing. Basically, you try to form a quantum system which is mapped to a real classical problem. For example, the optimization problem. How do you optimize the resources for a company? How do you optimize the investment profile for the investment portfolio? That can be used, that you can use the quantum annealing to find the optimum solution in a very fast time. It's better than classical annealing because it allows something like quantum tunneling of the states from a higher energy to a lower energy, right? So this is something we will not discuss, but you should pay attention to this. Companies, for example, like D-Wave, if you heard about this company, I think it was originally from Canada. You can pay attention to that for what they're doing, right? But anyway, these two models, gate-based and quantum annealing, will allow us to design the drug or material in a faster speed. Then, of course, they are important. Do computational fluid dynamic calculation, secure communication, quantum machine learning, and the financial service that I mentioned earlier. Right? So yes, it is very useful. If it is successful, of course, at this point, it's not really that successful yet, right? We'll understand why later also. So what is quantum computing? We can go from the basics. In classical computer, we know that we represent all the information by two states, 0 and 1. How do we do it physically? We can use coin, head and tail, happy and sad, or transistor, open and short, right? So we represent all the information by the state, okay? Quantum computing is the same, but it has some state that are more fundamental. We call it basis state. This is the basis of the so-called Hilbert space. Or you can think about the X hat, Y hat, Z hat in the 3D space. They are not the same, but it's just an analogy, right? So we can label it in the so-called direct bracket notation. When you see this, don't be afraid. Don't get scared, right? It is just a notation. Whatever inside this bracket, just to tell you the state is called 0, right? You can call it any name. You can use Japanese, German, French to write 0 or English, okay? And similarly, so you can also, in principle, you can use the head and tail to represent the basis states, head and happy and sad, or the transistor on and off, right? So it's no difference from classical computing. If you limit yourself to if you limit the quantum computing to only be able to process the basis state 0 and 1, you will find that they are exactly the same. What's important about quantum computing is that due to the physics, you might have some state which is a superposition of this basis state. So we can write it, again, this bracket notation. Don't get scared. I'm just saying that there's a state called psi. I put in the bracket notation. And it is a linear combination of alpha times the basis state 0 plus beta times basis state 1. It's just like your x vector in the space. Your vector v equal to a times x hat plus b times y hat. It's the same linear algebra, right? But here, the alpha and beta can be complex number, right? So what is this? What is a superposition state? That's all I can tell you, right? Because it's completely math. If you really want to have some feeling, you can say, maybe it's just like a spinning coin. I don't know whether it's head and tail. I call it a linear combination of head and tail, right? Of course, this is not a quantum computer, just an analogy. But the important thing that is you can have superposition. So why is a big deal to have a superposition? Now, let's look on the left. This is just a classical register. I guess some of you already learned this in your computer architecture. If I have a 4-bit, I can have 0, 0, 0, 0, 0, 0, 1 all the way to 1, 1, 1, 1. I can represent 16 states. In decimal, it is from 0 to 16. But I just told you that for quantum computer, it's exactly the same as a classical computer if we only care about the basis state. So we do have 16 basis states. Instead of just 0 and 1, you can have the basis states of 0, 1, 2, all the way to 15 if I have 4 qubits. But so that is what I'm saying here. However, because quantum computer allow you to have superposition, so I can also have states which is a linear combination of this. So if we look at this, if I have n qubit, I will have 2 to the power n basis states, 2 to the power n. For example, this is 4. 2 to the power 4, I have 16 basis states from 0 to 15 in decimal, right? Then I can have a state that is a linear combination of this. Then it means how many coefficient I have. It is going to be 2 to the power n coefficient. 4 qubits or 1 qubits give me 2 to the power 1, which is 2 coefficient. 4 qubits give me 2 to the power 4, which is 16 coefficient. What if I have 300 qubits? Then it has 2 to the power 300 coefficient, which is 10 to the power 90. What does it mean? In the universe, we have less than 10 to the power 82 atoms. And the total number of bytes we have in the world at this moment is less than 2 to 10 to the power 21. So if I want to describe one quantum state of 300 electrons, because each electron can have spin up and spin down, so 300 of them is just like I have 2 to the power 300 basis states. I want to describe them, I need 2 to the power 300 or 10 to the power 90 complex number. How do you store it? You even cannot store it in all the memory that we have in this world. This is not telling you the power of quantum computing yet. This is just telling you that a quantum state is so profound, a lot of information inside. You even cannot describe it easily with a classical computer. And that is the power of superposition. Okay. And why this is useful? Now, because quantum mechanics is linear, if I have this basis state, now I only have 2 qubits. You see that I have 3 basis states, 0, 1, 2, 3. I write it as decimal. Again, that is completely valid. I told you within the bracket, I can write anything, right? I can write your language or any language in the world, right? This written in decimal, it can be also written in 0, 0, 0, 1, 1, 0, and 1, 1. So this is a 2 qubit state, which expressed as a superposition of 4 basis states, right? 2 qubit give you 4, 2 to the power 2. Now, if I apply a function to this state, because it's linear, this function will apply to each state individually. Of course, it's not that simple, but this already shows us that I can compute each basis state in parallel with one operation if I can prepare the states as a superposition of the basis states. And that is the power of superposition, right? Just like in the movie, this is the multi-universe. Many world is evolving. Now, if I have 300 qubit, remember just 300 electrons, I have 2 to the power 300 basis states. I can compute 10 to the power 90 computation at the same time. Okay, it's not that easy, but if it can be realized, then that is why it's so powerful. That is the power of superposition and parallelism. Now then, I want to jump to another topic about measurement, right? We just say that the coin spinning can be considered as a linear combination of head and tail. Okay, now, how do you do the measurement? How do you know whether it's head and tail? You got to stop it, right? You stop it, it will become head or it may become tail. We call this what? Collapse. It's just like the wave function collapse. Collapse, where does it collapse to? It always collapses to the basis state, the measurement states, or we call it the computational basis. Okay, so that is the same for a quantum wave function. If we do the measurement, it may become 0 or 1. It's completely random. The only thing that has statistical meaning is that the probability that it will collapse to 0 is proportional to alpha square, the magnitude, the square of the magnitude of the coefficient. And the probability that you collapse to 1 is proportional to the magnitude of the square of the magnitude of the corresponding coefficient. And that's it. And no one can gamble whether it will collapse to 0 or 1 in the next, if you measure it. So that is the special thing about measurement. It's random, you cannot predict, and also it will collapse to the basis state. Okay. Then I will jump to another topic called entanglement state. So what is the meaning of entanglement? Now, I have a state. This is a superposition state, I just told you, because it is a linear combination of 4 basis states of how many qubits? Think about it. 0, 0, 0, 1, 1, 0, 1, 1. This is 2 qubits, right? Because I can have 0, 0 for the as the basis state, or 0, 1, 1, 0, or 1, 1, or 0, 1, 2, 3. Its coefficient of what? Half, negative half, because you multiply half to here, half, negative half. Now, for this state, it's not useful, not special in quantum computing. We can factorize it into the product states of the 2 electrons. So this system, 2 electrons, this particular state can be described as the description of individual subspace, individual as electron. Okay, this electron is in this superposition state, 0 plus 1. This electron is in the 0 minus 1 state. And these 2 electrons combined together, we call it a tensor product. We won't cover in this tutorial, but it's just how you form a larger space. It's just like multiplication. And I can describe that. So if I know electron 1, I know electron 2's description, then I describe the whole system successfully already. Nothing special. All this problem can be handled by classical computer easily. But there are some states, for example, this one, it is called entangled state. No matter how you do it, you cannot factorize it into the product states of 2 electrons. For example, this state only has 0, 0, and 1, 1 component. It also has 0, 1, 0, 1, and 1, 0, but their coefficient is 0. So you never will get this basis state if the wave function collapses. Okay, so that is one of them. Now, what's so special about entanglement, right? It's very important to help us to do the quantum communication and also some special algorithm, but it's too deep for us. We cannot go to those so deep, but we can look at some interesting factor, some interesting phenomena. If I have 2 electrons, I prepare them in an entanglement state. Okay, so up, up, and down, down. Just like 0, 0, and 1, 1, right? Again, you should be very comfortable now. I write it as up, up, and down, down. As I said, you can write in English, in French, or any language. Well, so why I cannot just write it as the arrow, as any symbol, right? I prepare it. Then I was very careful. I bring one of the electrons 100 light years away. It means the light need to travel 100 years to get to the other electron. I do it carefully. This system is still entangled, right? Nothing prevents them from being entangled. But now I will do a measurement. But how do? I just measure the electron on the Earth. Then, as I said, the electron can either spin up or spin down, collapse to 0 or 1. Okay, so let's say it collapsed to up. Okay, now if it collapsed to up, the whole system need to collapse also. I cannot just say that I measure this one, then the other one does not collapse, because the whole system is described by this wave function. And when the first electron is up, the other electron must be up also, because I don't have an up-down state in this entanglement state. Then it means if I measure up, I know immediately the other electron 100 light years away collapsed to up also. So that's what Einstein called the spooky action at a distance. So this is something very philosophical, but don't worry, it cannot change that does not affect the causality, right? That you cannot transmit the information faster than the speed of light. But that is enough for you to discuss with your friend for a whole day on how you can use it and why it doesn't work or whatever. Think about that. That is called quantum entanglement. Okay, so we learned the basic thing. We learned what is superposition, what is entanglement, what the measurement does. Then what is a quantum gate? So quantum gate is nothing. It is just something to rotate the vector in the corresponding hyperspace. I've been saying that, I say you can think about it as the 3D space in the superposition, right? It's just like V equal to A times X hat plus B times Y hat. You can think in that way, but that is not the space that the quantum qubit reside. It's just a description of its physics. And of course, in the physics, everything is math. So it is just a hyperspace that you cannot see, you cannot feel. But very often we map it to a so-called broad sphere. This is, we embed it in the 3D space, right? But it is really, it does not reside on the 3D space. But before we really understand them, just take it for granted. We say, okay, each state will reside on the broad sphere. When it is 0, it's on at the north pole. When it is 1, it's at the south pole. If you have a superposition, 0 plus 1 is here, 0 minus 1 is here. And any arbitrary state will be somewhere there. So when you apply a quantum gate, you actually rotate or move the points along this broad sphere. Okay, this is just an abstract description. But how do you do it physically? It is nothing but usually you just apply a laser pulse, a microwave pulse to the qubit. And that's why I say electrical engineer is are the important parts of the quantum computing. Who is going to generate the accurate microwave pulse? Who is going to generate the accurate laser pulse? You guys, you are going to design the circuit, FPGA, high-speed digital circuit, and then analog circuit, microwave circuit, right? You shoot a pulse to them, and then they rotate. So there are certain gates that has classical counterpart. That is not surprising because I told you that for the basis states, they're exactly the same as the classical one, right? 0 and 1, we have that in classical. We have NOT gates, 1 qubit gates, flip 0 to 1, 1 to 0. We also have control NOTs, 2 qubit gates, which is very important. It helps us to create entanglement, right? What it does is that I have 2 qubits, A and B. It can be 0, 0, 0, 1, 1, 0, 1, 1. And if the first qubit is 1, then I'm going to negate the second qubit because A exclusive B. If A is 1, it's just like not B, right? If A is 0, B is unchanged. So this is so-called control NOT. But you also have some gate. This you can implement in classical circuit easily. But there's something you don't have classical counterpart. For example, the Hadamard gate. You can create superposition. If the basis state is 0, it becomes a superposition of 0 and 1. If it is 1, it becomes 0 minus 1, right? You cannot have this in classical register. If it's 0, it's either 0 and 1. If you think it's a superposition of 0 and 1, then it means you have error, right? But this happens in quantum computer. Okay. So let's quickly take a look at this control NOT gate, just see how it does the entanglement. And I already told you that what it does is that you can operate on the basis. Again, this is 2 qubit, 0, 0, 1, 0, 0, 1, 1, 1, right? So for example, let's take this example. When the first qubit is 1, then the final result is you don't change the target qubit. This is control qubit, sorry, control qubit. But the target qubit will be the control qubit exclusive the target qubit because this is 1, 1 exclusive 0 is 1, so it becomes 1, 1. But for others, it doesn't change. Then you may say, this is useless. Why is it important? Because we can have superposition, right? So I can have a general state, which is alpha 0, 0, beta 0, 1, gamma 1, 0, delta 1, 1. Apply to it because it's linear, remember? So 0, 0 doesn't change, 0, 1 doesn't change. But 1, 0 becomes 1, 1, and 1, 1 becomes 1, 0. So it's just like you are flipping the coefficient from alpha delta becomes delta gamma. I mean, from gamma delta becomes delta gamma. So that is the entanglement gate. So how do we use this to create superposition? Well, we can prepare a state as 0, 0, right? I separate them, but this is a whole system, right? Again, why I don't write it as 0, 0 in one bracket? I can do that, but that's just a way to write it because this is just a symbol again, right? So this is the first qubit as 0, second qubit is 0. So we first go through the Hadamard gate. What does it do for Hadamard gate? If you forgot, it is create a superposition. If it's 0, it becomes 0 plus 1, right? So, okay, then this one becomes 0 plus 1, tensor product with 0. Okay, and this is just like regular multiplication, distribution law. So 0 goes in here, becomes 0, 0, and 1, 0. And then we go through this control NOT gate. What does it do? Again, if the control qubit, you do it one by one, the first one is 0, 0. Control qubit is 0, right? So you don't do anything to the next one. So it is still 0, 0. But here, the control qubit is 1. Then I'm going to negate the next one. It becomes 1, 1. Now, do you see that it is 0, 0 plus 1, 1, or up, up plus down, down? Then this is the entanglement. Okay, so I want you to have a feeling on how simple it can be just to create an entanglement. Okay. So as I said earlier, the quantum gate is very different from the classical one. The first thing is that they're reversible. Now, in classical computing, for example, a LAN gate, 3 different input can give you the same output. So I tell you, I have a gate, the output is 1. You don't know what the input is. It can be 0, 0, 0, 1, or 1, 0. But for quantum computing gate, it doesn't have this problem. If I know what type of gate this is control NOT, and you tell me the output is 0, 1, then I know the input must be 0, 1. And that is very simple. The reason is because, as you can infer from the name, is quantum computing. It uses quantum mechanics to do the computation. And quantum mechanics is physics, is reversible, right? If you go through the Schrödinger equation. So that's why all the quantum gates needs to be reversible. This is a good way. I always ask my students to check if they come up with a new idea, or when they do the exam and they find that their wave function collapse or whatever, then probably they did something wrong, right? It needs to be reversible. So this is a quantum circuit. You have a state, right? This state I did not tell you how to implement yet. It can be spin, it can be superconducting qubit. Go through the first quantum gate. Then what does it? What's the meaning of quantum gate again? It's a laser pulse or microwave pulse, and then the state evolve in their hyperspace, right? They rotate. Then apply another gate, rotates again. Of course, when you have many qubits, you use this to achieve your computation. And you can go back, because if you can rotate in one direction in the hyperspace, you can rotate back also. So it's reversible, unless you do the measurement. Once you do the measurement, wave function collapse, then it becomes the basis function. You cannot go back. But more importantly, I want to show you, this is the flow of time. We don't really lay out the gate on the circuit. On the other hand, on your chip, you only have the qubit. You shoot the microwave pulse, shoot the laser pulse, so I can have 1 trillion operation, but still having the same area of the chip, right? In classical computer, if you want to have 1 trillion operation, unless you're doing a looping, a feedback, then you need 1 trillion gates, right? So I hope that you won't be surprised later when people tell you, oh, for this Shor's algorithm or for this Rufus algorithm, we need to do 1 billion times. Then you may be very scared. Do I need to take out another chip with 1 billion gates? No. For the same qubit, we can use it for different algorithm. We just need to adjust the microwave and laser pulse. Again, who do that? Electrical engineer, right? Another important concept in quantum computing is error correction. It turns out that you can prove there's something called no-cloning theorem. It means you cannot copy the state. You cannot copy the arbitrary state. So if you have a state you don't know, alpha 0 plus beta 1, you cannot copy it. There's no mechanism for you to copy. It can be proved. Then that's a problem. In classical computer, we always use the measurement and also duplication to correct the error. For example, if I want to transmit 0, I make 3 0, then I use majority vote. If one of them got flipped, then but I know most of them are 0, then I assume it is 0. In quantum computer, you cannot do that because first, you cannot copy. Second, you cannot do measurement because once you measure it, the wave function collapses. You cannot continue to do the operation. So what we do is something called syndrome measurement. It's just like my energy might not be correct, but it's just like when I'm sick, right? I don't know whether I have a regular flu or I have COVID. I go to the doctor, they can really do the measurement, test the DNA of the virus, RNA of the virus, and find out what it is. But if the doctor is super smart or whatever, right? He knows or she knows some rule. They just ask how often I cough, what's the fever, how does it fluctuate? Maybe based on the syndrome, the doctor already know whether I have a regular flu or COVID, right? And that is what we do here. Sorry, I will come here to show you how you do it. For example, we will try to use entanglement to come up with a circuit. So this is the information we want. We don't want to destroy it. We don't want to measure it. But we add more qubit, which is called the ancillary bit. These qubit are very important, but useless at the end. So what we do is like this. For example, I have an information which is alpha 0 plus beta 1. I put it together with another 2 qubit, then it becomes 0, 0, 0, 1, 0, 0, right? Remember just the tensor product multiplication. Just 0, 0 multiplied to 0, and then 0, 0 multiplied to 1. Okay, so then what happened? I go through a control NOT gate, and then another control NOT gate. What does it say? It says if this qubit is 1, then you negate this bit. If this qubit is 1, you negate this bit, right? So this is 0. So I'm not going to do anything for the next 2 qubits. But this is 1 for this state, right? Then I'm going to negate that 1, 0, 0 become 1, 1, 1. Okay, so I form an entanglement. This is a little bit like the repetition code. Let's say there's an error. It flipped my code. So it flipped, let's say the first one, suppose it's 0, 1, right? Then it becomes 1, 0. Okay, this circuit is going to solve this problem. Why? Because I have another 2 control NOT gate again. So again, the first one is 1, so it's going to flip this 2 qubit, become 1, 1, 1. The first one is 0 for this one, then it becomes 0, 1, 1. Okay. At the end, I have something called control NOT, Toffoli gate. So this one you only flip if this both 2 qubit are 1, right? So if you look at here, these 2 are 1, these 2, the last 2, 1, 1. So this will become 0, right? And then these 2 are 1, so this will become 1. So I successfully revert to the original states, alpha 0 and beta 1. Yeah, the ancillary become 1, 1, but they are rubbish to me now. I will dump them away. But now, even I have the error, I successfully recover it. You can try it other flipping. You may be unlucky, they are flipping the auxiliary bit, but you find that you will always recover for this type of error. Of course, this is not enough, but just want you to get a feeling. Now, if you look at Google or something, some people talk about surface code, you need to add more auxiliary qubit, right? People talking about, I want to have an error-free qubit. And then it turned out you need to have 100 to 1,000 auxiliary qubit in order to have very high robustness to the error, any type of error. So people say if you have 1,000 logical qubit, then you can do very useful job. But however, it means you need about 1 million physical qubit, okay, in order to do some very useful job. And that is what's stopping us now at this moment. So I'm done with this part. Let me see how much time I have. Yeah. So let me just quickly go through an algorithm. I do not think that you can understand right away if you have not learned that before. But I just want to show you, give you a feeling of what quantum algorithm is about. There's something called Deutsch problem, not very useful, but it shows the quantum parallelism. So you assume you have a function that you don't know. This function can take 50 years, 100 years to calculate, right? For example, you have a chip. You want to verify whether chip is going to work or not. If it works, it is 0. It doesn't work, it is 1, right? That's an example. Now, our question is not this. Our question is asking, is this an even function, a constant function or balanced function? Constant means that no matter what the input is, you put in 1 or 0, the output is always 0 or always 1. Or balance means that no matter what you put in, the output is always half of them are 0, half of them are 1. This is useful in some optimization problem, okay? But the point is, if you ask yourself, classically, how do I do that? How do I check? I only have, here is only 1 bit, right? So how do I check if it is constant or balance? Well, I put in 0, calculate it, put in 1 and calculate it, right? And then I will know that whether it's constant or balance. So I need 2 computations, F0 and F1, if I don't know what the function is, right? But if I use quantum computing, I can do it in one shot, right? I have a video that go into the details. But anyway, what we need to do is to encode it into something called quantum oracle. Again, this one I don't have time to go into detail, but quantum oracle, after all, is nothing but just a quantum gate, a complicated quantum gate that your input is XY. XY can be 0, 0, 1, 0, 0, 1, 1, 1, or it can be multi-qubit, right? Not just 2 qubit. But the output is that X does not change, but the output is Y exclusive F of X. So quantum oracle is something that you encode the problem you want into here. But this problem, you don't know what exactly it is. It only gives you Y exclusive F of X. So it means you actually cannot calculate individual number, right? If you ask me what is F of 0, F of 1, I don't know. But by using this algorithm, I go through superposition state preparation and then make it into a superposition. I do quantum parallelism, and then eventually I do measurement, I will get it, right? So I won't go into detail because we don't have time, and also it's too much for you to digest. But basically, you see that we start with the basis state 0, 0, have a NOT gate, convert it to 0, 1, Hadamard gate, convert it to superposition. And that is because this superposition, you dump into the quantum oracle, it does the computation parallelly at the same time. And then we do the measurement. You will be very smart to come up with an algorithm such that if it is constant, it always gives you 0. So if I do the measurement, I get 0. I know that it must be constant. It cannot be balanced. If I get 1, it is balanced. This is nothing special to you. I think you understand it's possible to come up with algorithm so that if it is balanced, you get 0. When it is 1, you get when it is constant, you get 0, right? A balance give you 1, right? But I want you to appreciate this. Okay, so now let me share another screen that I want to show you how to, let me see, stop this presentation. And then I will share another screen that how to use IBM Q. For those who already use it, can you see my browser?
Yes, Professor, I can see that.
Okay, great. Yeah. So if you have not used it before, just go to IBM, type IBM Q, right? I'm not promoting for them. They are very slow now. We don't really have, but I think it's something very good. Okay, because I logged in already. Otherwise, you will ask you to create an account. It is free. I think if you use your school account, it will be better because sometimes I heard people use some like other account. They thought that it is like a spam, right? Then you go to this launch composer. And then you got this, right? So let me just create a new, it is very easy to use. I just create a new circuit and this represents different qubits, right? So I'm going to switch between my, you probably don't see it, right? I look at my slide. So it's just like the cheat sheet. I try to implement a very simple Deutsch algorithm. I put the NOT gate. Just in order to make it align with each other, I put the identity gate. I also put the break. This really doesn't matter. This doesn't do anything. I just put the break here. And actually, I realized I forgot the Hadamard gate. Click on it and then drag it. It's very easy, right? And then I put identity gate. Again, this is the quantum oracle. Again, I don't have time to go to the detail. You can watch my video if you're interested or the book. But this corresponds to one of the most basic balance example, right? When the function is balanced. Then I put Hadamard gate and then I do the measurement. So because this is only 2 qubit, I'm going to right click, click on this and then delete the left click and then delete the other qubit, right? This classical qubit means when you do measuring, it's going to store the result in the classical qubit because I only have 2, so I'm going to reduce it to 2. And then I'm done. So I can, on the right, you have the corresponding command, which you can use the Jupyter Notebook Lite interface to run them. This is just an example. You want to do looping or whatever, you want to use this. So there are different type of command. I think this one should be Quasam. Yeah, you want to use Qiskit. This is better. Qiskit. Just set up and run. Now you can use this quantum computer. They're real quantum computer here, right? But because of time, I will explain to you why. I just submit to the simulator. This simulator are nothing but just the simulator. Use classical computer to simulate your result, and it's very quick. The job already done, right? Then let's look at the results. What is this? Yeah. So now you look at this. All of this is 0, right? Because this is a constant function, it gives me 0. Because of time, I already ran this in a real computer also. Now I go to another tab. This is the computer I submitted this morning to IBM Qto. You see that I need to wait for 7 minutes because of the queue. And then eventually I get the result. And let's look at the result. The simulator give me 0, 0, but here I get 1, 0. What does it mean? You try to run many times, right? And then sometimes it gives 1 instead of 0. Anyone know why? Any suggestion? Why in the simulator is this? By putting the real computer, it becomes sometimes 1 and sometimes 0. Anyone want to answer?
Because of superposition, I guess, sir.
Because of the superposition? Or you say because of the error? But anyway, thanks for answering. I think it's a little bit slow, the internet. You're right, because of the error, right? Because in real quantum computer, you can have error. And think about this. This is a very simple operation. When you go to 1000 qubit, you will get tons of error. Okay, so that is the problem. Okay, so now I will go back to my original slide and share again. Right, I just want you to have a feeling for those who didn't have this experience. So what did we learn so far? I know if you did not study before, probably it's too much for you, but really want you to have this concept. The problem are encoded in the quantum oracle. You need to find a way to encode them. This is a difficult part. And then, because you don't know what the problem is, if you already know the problem is, you probably know the answer, right? And the important thing is, see that quantum computer, sometimes people say, wow, it is so fast. Looks like we gain a lot from the God or from the nature. But no, in my view, it's something like conservation of information. We only know whether it's balanced or constant, but we still don't know what is f of 0 and f of 1. We gave out those information because we only care about whether it's constant or balanced. So you cannot replace the classical computer if you are interested in knowing whether it is what is f0 and what is f1, right? So I say quantum computing just show another path to find the answer. And for me, it doesn't contradict the common sense, right? Or just like entanglement, it does not transmit information faster than the speed of light. But you already see that we need superposition for quantum parallelism. And we also need entanglement. And that's why, and measurement, right? So these are something people play with to get the information. So let me talk about the hardware, right? I don't have much time, I know, but I only have maybe a few more slides. I again want you to have a feeling. To have a successful quantum computer, you need 5 criteria. The first thing, the qubit. We talk about 0 and 1. Your physics need to give me 2 levels. You cannot give me more than 2 levels. If their spacing is the same, then when I apply the microwave pulse, you go from 0 to 1, 1 to 2, 2 to 3. I'm talking about 1 qubit, not 2 qubit. Then left my Hilbert space, right? What is the meaning of 2 in my 0, 1 space, right? In my binary space, it's meaningless. So it is need to be scalable. You need to be able to make many qubits, right? Also, if you have pay attention to the algorithm, I show you all start with 0, 0, because we need to have an initialized state. And it's very often we need to initialize the qubit very often in many algorithms, many times. If you take 1 hour to do the initialization, then maybe it's useless, your quantum computer. Long coherence time, let's discuss it a little bit more. But basically, it says that you do not lose the information before the gates finish. The gate, right? Your microwave pulse has a certain time, 100 nanosecond, 1 microsecond. Then you better to have at least 100 microseconds before the information loss. And we also need to have the universal set of quantum gates, right? In classical logic, we say either NOR plus LAN, NOT plus LAN, NOT plus OR you have NOR or NAND, then you can build any of the circuit. Same here. You need at least have a good entanglement gates and then many, some of the important 1 qubit gates, okay? And also, I should be able to measure the qubit individually, right? When I do measurement, I don't want everything to collapse, right? So these are the 5 criteria. We also have criteria for quantum communication, but I will skip here, right? So how do we implement? Of course, just for fun, you can say, how are you today? 50% happy, 50% sad. And I think in order to describe quantum computing, you really need emotional thing. You cannot use physical thing, right? We can use spin qubit. We confine 1 electron and then apply an magnetic field. If spin up, lower energy, spin down, lower energy, spin up, higher energy, then it becomes a superposition of these 2 spin states. Photonic qubit, there are many ways. One of them is that I have an identical path. I shoot 1 photon to here, they're connected, 1 photon flying from here, and then I ask you, where is the photon? You probably don't know because they're identical. You may say 50% on the top, 50% at the bottom, or 30%. So it's a superposition of the path. But once you measure it, because there's only 1 photon, if you get it here, then it must be here. If you don't get it here, then it must be here. Wave function collapse. Superconducting qubit is another thing that is very common. And what we do is have something called Josephson junction. Again, you can watch my video or just Google Wikipedia. Coupled with a capacitor, it depends on how many extra Cooper pairs in this island. Between Josephson junction and this capacitor. We use this microwave pulse to control it, to rotate it by coupling through this capacitor, right? So you can say it has 50% chance of 0 extra Cooper pair, 70% chance of 1 extra Cooper pair, right? 1 Cooper pair is a pair of electrons. At very low temperature, when your electrical circuit becomes superconducting, all the electrons will pair up and it becomes a macroscopic object. Okay. I guess this is my almost final slide about the noise and coherence time. And as we just said, the divisional criteria is that you need to have a well-separated level, but you will see that most of them are very tiny separator. For example, it can be like only, what is this? 0.02 milli electron volt, right? Correspond to 0.25 Kelvin. And your thermal energy at room temperature is already 26 milli electron volt. Then, of course, you cannot separate them. You cannot distinguish them. That's why we usually go to diversion refrigerator or use laser cooling. And there are 2 types of decoherence times. You may flip the bit. This is T1, start from 1. Then it takes certain time. Maybe here, this is a superconducting qubit. This is a real one. It may take 290 microseconds to flip. Then you lose all the information. Or defacing time, which is D2. You are in superposition 0 plus 1. But it becomes, I don't know, 0 minus 1 or whatever. Alpha, beta is changed. It's still superposition. But again, this is useless, right? Because we rely on superposition to do computation. So this one it's usually shorter. This is only 19 microseconds. Then it means your gate better, for each of the gates, better to operate within 0.1 microsecond. So I can apply about 100 or 50 gates before it dies, right? So that is the final slide of this talk, right? We've sure that quantum computing has a lot of information, a lot of coefficient here, but we cannot get them. 2 to the power 30, 2 to the power 300 compressed coefficient. How can you get this? You can only do this by measurement, by measuring many times, and at the same time, you only know their magnitude square. So we need to be smart. So what we do is we use some destructive and constructive interference, like what we saw in the Deutsch algorithm, that it will tell us whether the function is balanced and what is the period of the function, which is useful for us to solve some complicated problem. So quantum computing cannot replace classical computing. Do not imagine that it is going to help you to calculate 1000 by 1000 faster than your laptop, but it will be a very useful, powerful accelerator. And we only need them for difficult problem, like optimization problem. Otherwise, other problem, Excel window are good enough, right? So I think it will be a good accelerator, okay? Finally, if you're really interested in quantum computing, you can read my book, but at the same time, I really feel that you need to go through the math, right? So like in this paper, he said, shut up and calculate, because in some sense, we really don't understand quantum physics, right? Yes, we don't have daily experience. Yeah, so that's all my talk. And again, you can find the book and the YouTube here. Thank you very much.
Thank you, Professor, for such an informative session. So we have some questions in the comment box if you don't mind answering.
Okay. I cannot find. Okay, I see here. How are the quantum circuit realized practically? So I just I mentioned it at the end, right? So for example, you can have a superconducting qubit, and then so for example, you can just print the transmon circuit there. What I showed you earlier, right? You can have a Josephson junction. That is just a superconductor, insulator, superconductor capacitor. So print it as a capacitor on the chip. That is a qubit already. Now, then how about the circuit? Well, you need to lay out some microwave lines, right? Resonator, transmission line, termination. Send your pulse so they can feel it. That is how you realize that for superconducting qubit. How about trapped ion? Trapped ion, they really put it in vacuum. They use the electric field, throw the ion in the vacuum one by one, and then you shine the laser pulse to rotate the ion. Not really physically rotating. Again, it rotates the state, the spin, right? Not spin, right? For trapped ion, not the spin, but the it's related to the spin, the coupling between the nuclear spin, but rotate the states. Not so for trapped ion, you have a ground state and excited state, but the ground state and excited state are due to something called hyperfine structure. You probably learned in your chemistry, and that hyperfine structure is due to the magnetic moment of the nucleus and also the electron charge, right? So then you have two different states. You shine the laser, then you make the electron state to be a superposition between the lower level and higher level. This can be mapped to a hyperspace. So they are rotating the hyperspace like this, okay? So if by measurement destroy superposition, how do we get control useful? Yeah, so now I already show you, you don't get useful output until you come up with a smart algorithm. Like in the Deutsch algorithm I just showed you, we arrange it so that if I get 0, I know that it is constant. If I get 1, I know it is balanced, right? And that's why you cannot use it for regular computation. But this is good enough because this is a difficult problem. I can do parallel computation, right? And can you briefly explain the black swan forecasting theorem? So the black swan forecasting is more like optimization problem. So in your financial investment, right, you always need to focus what is going on. But after all, this is nothing but just optimization. I don't know this well. So this is just like if you can optimize the problem, you can map the problem to the quantum annular, then they will find out what is the best portfolio. And at the same time, I don't know how you do the Black-Swan forecasting, but I think that they are related. So yeah, so it's again related to optimization. How does quantum computing intersect with machine learning and artificial intelligence? Yeah, so this also related to optimization. So for quantum machine learning, that is, you know, for machine learning, the most difficult part, right, the most time-consuming part is the what do you call the the training, right? The finding of the all those weights and in the neural network, right? So what they do is this, right? You can try to that is an optimization problem again. So one possibility is that you create something called the answer for that problem. And this answer actually is difficult to create again. Again, it's not straightforward. It's not unlike machine learning. You learn from class. This is the way to create a neural network. You need even this is an actively researched topic, right? But assume this answer can help you to find a certain parameter. Then you get this parameter that will minimize the energy of a certain certain Hamiltonian, right? And then you get that, and then they will use a classical computer to do the gradient descent, and then come back with another theta, and then they will do the calculation very fast to find out whether it's close to the minimum energy, and then go to the classical computer again. So usually the main part for quantum machine learning is to use the quantum computing part to calculate the minimum energy again. Okay, so to perform this very intensive matrix, not exactly matrix multiplication, but to achieve the goal of doing the multiplication. Okay, so since it's sensitive of noise, how effective it is, right? It is difficult. So that's why I said, if you want to get a really usable, what we call fault tolerant qubit, you need 100 to 1,000 physical qubit to do the error correction. Then you will be insensitive to noise. Yeah. So I think I only see this question, right? No more questions.
Okay, so this brings us to the end of our session. Professor, thank you so much for accepting our invite. We are truly honored to have you as our speaker today. Yeah, quantum computing is not a usual major in our country, but I hope this session would be a driving force to break the stigma.